I still have that window open? Is this us? Oh no, we're using Cloud9, right? Yeah. That's a online C compiler, but it doesn't. You can't run it. You can't attach an IP address and stuff like that. This is yeah, grad class 540, 548. This is 2's complement code. It's not that bad. It's all the same crap. Why? Is this a confession? Bakari, will you hit the third button down, please? Because what did you do?
I don't know how to use a gas stove.
Okay. So you left the gas on too long to let the whole house fill up, and then you lit it?
I suggested we light a match. I don't know how to use a gas stove.
So did you guys light it?
Did we? No, it was like, I thought I turned it off, but I didn't.
Oh, so the whole house so you had the smell. Did it smell like the rotten eggs? You know, they add that to the natural gas. The rotten egg smell is not part of, natural gas is odorless.
You should have asked for a stove without that smell.
Well, no, you don't want that. Because if you had it without that smell, then you wouldn't know that your entire house was filled up with this stuff. And the first time you get shocked on a doorknob, the whole house lights up. You don't want that. You want the smell. The smell is there for your protection.
Oh, I didn't know. See, I don't know what's going on.
My dad actually can't smell. And my brother walked into the house one time and he's like, is your stove on? And I guess it's been on for like hours. I think my mom was there too, and she can smell. Only one of my parents can smell, but she didn't know.
See, this happened to us. We had a guy come out to check our chimney. We have 2 gas fireplaces at the house. So my wife's afraid of the fire or whatever, so she wants to have this thing checked every 15 minutes. So this guy came out and he didn't think the gas was on. He couldn't hear it. So he turns it on, doesn't think it's on. I mean, this is like supposed to be the professional, right? He's running downstairs, checking her gas line. Everything looks like it's fine. Comes back up there and decides, doesn't even think it, just lights a match. But like, oh, his eyebrows were gone. Just, and then he still bills us. Yeah, he says, "Oh, it looks like it works." Never trust a professional. Okay, let's see. Visited services. Live. All right, so last time we were looking, I had given you some starter code for our server, and we ran our server. We saw we had 2 different terminals running. All right, connect. Big money. Okay, yeah, so we have 2 different servers running here. This guy's running on port 8080. When it first launches, if I remember correctly, this is the address that we had running. Let's just make sure we're on the same address. So I'm going to do if config. Is it IP config?
No, it doesn't have an in it. It's config, not config.
Oh, I just spelled it wrong?
Yeah.
Is that right?
Yep.
Nailed it. All right, so that's our IP address for this guy. So just to give you an idea here, do I have, here's our error HTML, right? So when we start up our server is listening on port 8080. It's going to take in a get space. Actually, we don't have it taken in a get yet, right? Because our server is reading something. And so we need to modify this guy a little bit. So let's walk through the server again real quick. So these are our pieces for our socket. Here's the file descriptor for our server. The new socket is the incoming guy. The value red is going to be a pointer to the beginning of that. Jeez. We have the socket address in. So this is a struct that comes from socket.h. And we'll see the pieces of that here in a second. We saw it last time. The address length, that's the size of whatever that struct is. Here's our buffer for reading stuff in. Here's the message we're going to send back out, stored in a char pointer. So now we're doing, this is a whole bunch of error checking stuff, which we're typically not used to doing. We typically omit the error checking, but first thing we're trying to do is we're trying to create a new socket for all internet addresses, and this is going to be a socket stream. What's the difference between a stream socket and a datagram socket? Go ahead.
Stream socket cares about whether it actually got the message.
Okay, so this guy's governed by TCP versus datagram is governed by UDP. So UDP is what you use for like video streaming and stuff like that, where it would be acceptable have like a dropped a dropped frame or something like that, where if we're transferring a big file, we want it to all get there. All right, so this little if statement says, hey, look, we're going to try to do this. And this function, this socket function, returns a 0 if something bad happened, or something other than 0 otherwise. All right, so we're going to say, try to create a, let's think of it as an instance of socket. Well, really, it's not an instance. It's actually just creating the file descriptor to where that socket lives. So it's calling the socket function, which is going to take in some options. So we're creating this kind of, well, we're creating a socket that can accept any kind of connection from any source on the internet. It's going to be this kind of socket. And let's look real quick. I want to see what that last piece is. Protocol. So the domain for it, the type, and the protocol. So here's the possible domains. There should be an AF all somewhere. These are all internal. Oh, this is using a slightly different thing. So we're using AF Unix or AF INET versus PF INET. So this must just be a little bit different version of. So these are BSD system calls for it, where the Unix it's probably a Linux based operating system that we're running on the Cloud9. So but these guys are effectively macros that are coming with socket.h. that allow us to, that puts in some value that is the equivalent value for that option. All right, so this is the domain, specifies a communication domain within which communication will take place. And this selects the protocol family which should be used. For example, whether or not it needs to use IP address based stuff or can use domain name based stuff, that kind of thing. All right, so those are our options there. Then we have the next piece of it, which is the type. So we have socket stream, socket datagram, and then socket raw, which is just going to be just raw bits coming across it, not governed by anything, or assumed to not be governed by anything. It very well might be governed by whoever's starting to send it, but this guy's not going to try to re-request information or something like that. He's just saying, I'm receiving bits, not packets, not anything else. That's more of a networking type thing. Okay. And then does it tell us about that last piece? So the last piece is supposed to be an int protocol. All right, so protocol specifies a particular protocol to be used with the socket. Normally only a single protocol exists to support a particular socket type with a given protocol family. However, it is possible that many protocols may exist, in which case a particular protocol must be specified in this manner. The protocol number to be used in particular to the communication domain in which communication is to take place. See protocols. All right, so we could do a man protocols. And it's showing us that there's a file here called Etsy protocols. So I'm going to copy that. I should be able to do cat Etsy protocols. So here's a list of all the protocols that our system understands. But they said for socket protocols, there's only one, and I think it's passing a 0 there. So this is just the normal IP protocol. So I think we had a 0 passed in, right? Yeah. So protocol is IP. TCP over IP. So this says use TCP to guarantee the delivery. This says use the standard protocol, which is IP. Okay, that's internet protocol. All right, make sense? And just real quick, we can get the, if I quit this. Anybody remember what the man command gives you? What does that guy stand for? Manual. Yep. So any Unix system has a command called man that you can kind of help get a search for different things. So man socket. I go down to the PFINet, which is equivalent to the AFINet. This is Internet version 4 protocols, which is all internet. Right? So that's all the internet. And this is IPv4 as opposed to IPv6. Here's IPv6. Anybody know what the difference is between IPv4 and IPv6? Go ahead.
IPv4 only has like 4 billion IP addresses available, whereas IPv6
Has more.
Way more than that.
Yeah, so if you look at an IPv4 address, your range of values is 0 to 255. So we have, so 0 to 255 is a unsigned 8-bit value, right? So this is 8 bits followed by a dot, followed by 8 bits, followed by a dot, followed by 8 bits, followed by a dot, followed by 8 bits. So that's a total of 32 bits address space for your for IP addresses, which means that you have 2 to the 32nd IP addresses, or as she pointed out, about 4 billion. So 2 to the 32nd is 4.2 billion. Let's put that there because obviously I had that memorized. Nailed it. All right, so that's what you have for IPv4. In fact, I'm going to IPv6 is 16 bits followed by 16 bits followed by 16 bits followed by 16 bits for a total of 64 bits. So that is 2 to the 64th power, which is what, like 16 quadrillion, I think? 2 to the 64th, 18 quadrillion. That. So we have 1.84 times 10 to the 19th power unique IP addresses. Why did they come out with IPv6? What's the reason for that? Go ahead.
Because we're running out, like, because there's so many devices everybody's using that, and especially like more like the smart devices, like you're talking about cinematics, like fridges and stuff like that. Everything's
Yeah, all that's true. We are running out, but we're not running out just because we have so many devices using it. That's certainly exaggerating a thing. Anybody know what the other reason we're also running out? The other reason why we're running out? So when we get an IP address here, So if I do IP, where is it? If config. So my IP address, what does Apple hide it? No, it's right here. All right, so that's my IP address here. So this 172 dealio. So do you know, or is every address here on campus starts with a 172, right? Does it also start with a 31? Okay. This number changes. The 234 changes. We have a couple different ones. Okay. So when Concordia, so in the early days of the internet, or even now, this would happen now, when you create a network that you want to be on the internet, routable, these are routable IP addresses. What you have to do is you have to request a block of internet addresses. Right? So what they've done is they've assigned us a block of internet addresses. So we have 172.31, so those are fixed bits for us. So now, even if they gave us the entire rest of the space, that would give us 16 bits of unique addresses, right? But chances are they have not done that. Do you know how many different unique things we have here? Have you seen more than 3?
Not that I can recall.
Okay, so let's say they've given us 3 of these. Okay, so they've only given us 3 of these guys. So even though there's 256 possible of these, we only have 3 of them. Okay, but we have all 255 or 256 of these. So that means we have 2 to the 8th power times 3 is the number of unique IP addresses we have on campus. So 2 to the 8th is 256 times 3 is 768 IP addresses on campus. Now, do we have more than 768 machines on campus? Okay, then they probably give us more.
I think we have quite a few. And like where it's 2, 3, 4. I'm pretty sure we have a lot.
Okay, so whatever it is. Yeah, but they gave us some piece of that space, and then they gave us all of the last one within that space. Okay, so they effectively handed Concordia a portion of the full address space and said, "This is yours." Make sense? So let's assume that whatever they've given us, let's say we have 10,000 possible IP addresses. Is that more than cover the number of IP addresses we use? Okay, so we'll just gonna use some rough numbers here just to say. So let's say they've handed us 10,000 unique IP addresses that are earmarked for us, but let's say that we only use 2,000 of them. That means that we have 8,000 IP addresses that are completely unused here that nobody else can use. Does that make sense? So now, do that across the entire internet. Every company that has IP addresses assigned to them, you have all these IP addresses that go completely unused but can't be used by somebody else because of the way they're handed out. Because when you request IP addresses, you say, "Oh, I need this many IP addresses." That kind of makes sense?
Is there ever a point where they would just start limiting how many of your IP addresses that you're requesting?
Well, I think they do a better job of that now when you do request an IP address. And I think when companies, you also had during the .com craze, you had a bunch of companies that were started, got IP addresses, failed, never gave them back. Because there were so many companies failing that it was just kind of lost in the paperwork. So they're a little bit better about it now, but the point is that we're running low on 32-bit IP addresses, not because we necessarily have 2 to the 34th number of machines in the world that are running. We're probably getting interestingly close to that, of having 4 billion computers with unique IP addresses. But we got to consider a lot of the machines that we have at any point in time have non-routable IP addresses. So if you're at home, your IP address is like 10.0.0.5 or something like that, where at my house, I might have that exact same IP address. Okay, but so only my router in the house has a potentially a real IP address, but it might even have a 10 dot number that was handed to me by the cable company or something like that. Okay, so we do have some things in the middle that try to help us limit the amount of extra IP addresses that we're using. But at the very least, we have, as Alexis pointed out, we have a zillion mobile devices and computers that all want IP addresses, and at least some of them are getting real IP addresses, and that's going to start adding up. right? So this whole IPv6 thing came out to try to help this problem. They said, we're going to give you twice as much bit space for your IP addresses. But are we using this yet? We're kind of on that cusp right now. So for instance, I'm not sure if Google's doing the same thing. My suspicion is they're not because that they just enforce differently. But Apple is just definitely doing this when you submit an app to the Apple App Store. It has to, any network stuff you do with it has to be IPv6 compatible, and they'll test it against that. You kind of have an issue right now where you have a couple of the big companies that are starting to push it, but we're pretty used to IPv4. We don't really want to move away from it. So we're in that transition where we almost have to. We don't quite have to yet, but sooner rather than later, we're going to have to jump ship and move over to IPv6. And then what you'll have is you'll have the companies that currently have IP addresses. They'll have the same IP address. It'll just be prefaced with zeros in that bit space. And then you'll have new bit space created for more addresses. That makes sense? So in any case, the default on our operating system here is IPv4, as it will be on every operating system right now. That will be the default. You would have to switch on IPv6 as your default one otherwise. Does that make sense? All right, so that's the difference there. So we were looking at AFINet, right? Which is equivalent to PFINet. So that's IPv4 versus IPv6. So we're using IPv4 for all internet traffic. Okay. Going back to this, socket streams TCP IP, and this is over IP. So this says use TCP. This says use IP as the protocol. Make sense? Okay. So when we do this, this function call is going to return a value. It's going to return an integer, either 0 if it worked, or some other, or 0 if it didn't work, or some other value, probably a 1 if it worked. Okay? So this value, this will boil down to an int. That int will get stored inside of this server FD. What's in parentheses right here will boil down to the value that lives in server FD. And we're checking, is that value equal to 0? Make sense? This is something we might not necessarily be used to in a lot of our, in some of our high-level programming that we've done, is we're not used to necessarily making function calls and assignments all inside of an if statement, right? And part of that is because, part of it's because a lot of our current stuff, function calls, aren't giving us error messages back. They're using exception handling for our error messages. In this case, this is pretty common in C. I'm doing an assignment right here. Well, I'm doing a function call, which has a result. I'm assigning that function call's result to that variable, and then I'm also checking the value of that variable all at the same time. Make sense? Everybody good with reading that? All right. So if something went wrong, spit out socket failed, and then program ends. And exit failure is going to give a 0, probably the default output, I would assume. All right, so assuming we're still alive, because if we got past this if statement, that means we didn't get kicked out, then we're going to attach the socket to port 80, or 8080. All right, so we're going to set some socket options. So this is another function call. So let's go and look at set sock opt. So here's set sock opt. This guy takes in, so this is inside of socket.h. And here's that function. Takes in the file descriptor for the socket, takes in something called a level, an option name, a pointer to an option value, and then this guy is going to be a struct for option, a struct, this would be the length of our option type. And we'll see it here in a second. Let's see if they give us good breakdowns there. We'll look at the code. So here's our file descriptor. So SOL socket. Now, right here, this is an interesting piece. We'll look at that here in a second. So let's look at this SOL socket. Maybe have an SO socket. Oh, socket layer. So this is when you have the TCP/IP stack. So TCP/IP is actually a 5-layer stack. So one of those is the socket layer, and that socket layer is what they're referring to here. And that guy goes into the position for level. So what level of the stack? All right. Now we have a bunch of options. All right. So we come in here for these options. We have an option there, so that's a SO reusable address, and we were just looking at those things over here. So if I scroll down a little bit, here's SO reusable address. This enables local address reuse. So if you run the program multiple times, it'll let you release the address and then regain the address. This other guy is reuse port. Same thing. It'll allow you to reuse the same port, 8080. So here's reuse port, enables duplicate address and port bindings. That way, when you kill your program and restart it, it'll allow you to re-grab those the same address and the same port number. But notice we have this piece here in the middle. What is that guy? It is the pipe. What does it mean in this particular case? We're used to seeing 2 pipes, right? If I had 2 pipes in there, what does that guy say? That's an OR. What's 1 pipe? It's a bitwise OR. Okay, so what does bitwise mean? If I do bitwise operations, I know we're going through this at a very granular level, but this will help us in the future. Because now we're learning how to read these C functions. Okay? So bitwise OR. In C-type languages, that's a single pipe like that. Okay, so that will give us this will work in Java, for example. So this assumes we have 2 binary values. So for instance, let's just say we have a nibble size value. How big is a nibble? If you haven't had 325 yet, you might not know. Yeah, it's 4 bits. Okay, so a nibble is 4 bytes, or 4 bits rather. And so let's just say 1100. So these are my 2 nibbles. So this might be my first option. This is the reuse address, and this is the reuse port. I'm literally just making up numbers, but let's assume those were the 2 options. A bitwise OR does the OR function, but on each individual bit. So for an OR to be true, at least one side needs to be true. So we have to have at least 1, 1. So ORs are true if we have a 1, 1, a 0, 1, or a 1, 0. The only time an OR is not true is if we have 2 zeros. So 1 OR 1 is 1, 0 OR 1 is 1, 1 OR 0 is 1, 1 OR 0 is 1. This is the result of bitwise ORing these guys together. Okay, so this right here will map to a particular option collection. All right, so if you chose every single one of the options, for example, and you ORed all those together, you would have a pattern. And that final pattern would mimic, the address space, I'm sure, is bigger than 4 because there's enough options. Where are we at here? There seems to be enough crap here. I mean, potentially you could OR all those together. There might be some that are in conflict, but let's assume you could OR all those together, right? That must mean that the address space for this must be large enough to house that. And it probably, does it tell us what kind of type it is? Yeah, it's an int. So that's going to be 32 bits. So we have a 32-bit address space. So there are 2 to the 32, in terms of the space we have, possible combinations of options. I doubt there's that many combinations of options related to these, but there's going to be more than 3 or 4, right? So maybe there's, I don't know, 600 combinations. I'm just pulling that number out of the sky. We actually could probably figure it out, but whatever. Let's just roll with that. Okay? Big Bang Theory. Like, is that a rhetorical question, or would you like to do the math? Have you heard that part?
Do the math.
Let's do the math. All right, so in any case, we're choosing these 2 options, and we're bitwise ORing them together to give us the option collection for that particular guy, which is going to be some number that will map to the collection of all those options. Make sense? All right. So you'll see that pretty often in older C stuff when you have, and not just older stuff, but you'll see it often in older stuff, when you have multiple things you need to pass in and you want to do it as a single parameter. All right. So this is related to masking. There's a technology called masking. We see it like in networking with subnet masks, where you take a value or a collection of values and you almost encrypt it. It's a weak encryption, but you kind of encrypt it into something else, and the weak encryption we're calling masking. Okay, and then this guy, this address, this value, it's not an address in this case, this value, then would map to, like, oh, this is the collection of things you chose. Make sense? Okay. Then we're giving it the address of opt. And what's opt? Opt is this value number 1. So we just created an opt called number 1. What's that supposed to be in here? This guy is our option value. And what does the option value relate to? It doesn't tell me what the option value is. Maybe that's the return type for it. Typically, a function would pass in the address to something if that guy is going to be changed. Because this is essentially saying we are passing by address. So if you remember way back when I kind of explained the difference between C++ and Java, is I mentioned that C++ allows the programmer to, empowers the programmer to make bad decisions, right? Because they have full control over memory. This is our way of saying, okay, I need to have a value when this is done, but I'm not going to return that value from socket opt here. Why might that be true here? Why might we set sock opt? This function returns a value, right? And the value seems to be something that if can ask a question about. So it must be a Boolean expression that guy returns, which in C and C++ is an int, 0 or not 0. Usually it's 0 or 1. All right, so this function returns a value in terms of whether it was successfully run. Make sense? But now I also might want another value to come out of there. I want to know the success level of my options. So by passing in the address of my variable OPT, when that function is done being called, this variable's value may have changed, because this function had direct access to it. Now, I didn't see in the man page how it could change. It maybe is in here somewhere, but I didn't happen to see it. But at the very least, the evidence would suggest, since you are passing this guy in by address, that is a value that this function intends to at least potentially modify, because you're giving it the you're passing opt by address instead of by value, which means changes to it would happen globally. All right, so after this if statement, for example, I would be able to look at opt, the value that lives in opt, and see what its value is now post calling set socket sock ops. All right, and this guy's, his value might have some meaning. It's possible they use it here in a few minutes. All right, and then we're also passing it the size of opt, which in this case I think it was an int, so that's going to be the size of an integer. Okay. All right, so does this guy make sense? So we're trying to connect to, actually it has not connected to port 80 yet, but we're trying to set our options on this guy first. Assuming we're still alive after that, because we have an exit in here, so that throws us out of the program. So assuming we're alive after that, we're setting the family for this address to AFINet. We've already seen that before. We're setting the S address. So we're working with the address struct here. So here's address. This guy is a sock address in. So if we go look at this dude, no. It's included in one of the man pages there. This will be an easier way to find it. It's in in.h. All right, here's our struct for sock address in. All right, you're starting to see the value of jumping around and looking at this stuff, because this is how you would have had to do it in older C programming. You don't have like a single place for all your documentation. All right, so this is what this struct looks like. It holds 3 pieces of information. It holds the address family. It holds the port in network byte order. So this is the port we're connecting to. And then it holds the internet address. So these 3 pieces of information. We go back here, we should be in here. So there's the family will accept any address, any incoming address. And here's our port, which we stored 8080 in up here, wherever it is, port 8080. And this guy's called the macro. So we stored the port in 8080 and HTONS. It's going to be hex 2. Convert values between host. Oh, this is host and network byte order. So H2NS. So this is host 2. What does the NS part stand for? I want to be able to tell you what it actually stands for. Okay, so it converts from host byte order to network byte order. So I'm not sure it actually tells us what the S stands for, but it converts it to here. Host byte order to network. What does the S stand for? Don't know what the S stands for.
For short, because looking at the ones that end with an L, it's referring to a net long versus a net short.
Oh, could be. So that would be a 16-bit value instead of a 64-bit value. Possible. All right, so it's taking our port 8080 and converting it into a number in the correct format that this guy takes. Okay, so we're assigning that to the sign port of this struct. So notice that we work with structs similar to how we access objects. So these are almost like public fields in an object, right? So we're taking our instance of our struct called address and setting its sign port equal to this, its address to any address, and its family to this guy. So we're just filling in values in that struct. Make sense? Finally, we're going to attach this to port 8080. So we're going to call a function called bind. Go back out here. We do man bind. It's going to be bind is going to bind you to an address at a particular port. So we're binding to this file descriptor, that's our socket, and we're passing in the address of our struct. So remember back I mentioned that by default structs are passed by value. So we're passing in the address to the struct, so this guy potentially could be changed as a result of this. Whether or not it actually does get changed or not is something different. All right, then we're passing in the size of that struct, and we're checking this entire thing to see if it returns something less than 0. All right, so for bind, less than 0 is a failed value. 0 or greater is a positive. So we already see some inconsistencies, right? Before that, we were looking for it being equal to 0 up here. And that was considered failing. Now down here, bind happens to return a value less than 0 if it failed. Or presumably 0 or greater if it doesn't fail. Less than 0 means that it might return values that are -1, -2, -30. Why might it return different values less than 0? Go ahead.
Tell you different things that went wrong when it was binding.
Okay, so old school exception handling without the exception handling, right? So this guy's going to return some error code. We've seen it in websites before, like 404, file not found, that kind of stuff. So this guy might return some number less than 0, and each of those numbers might be meaningful. They might mean this is what actually went wrong. Okay? So they're just saying bind failed. But if you really wanted to know what's wrong here, you maybe want to store the return value in a variable and print that out here so you can find out why the bind failed. What error message was actually returned from it to give you some idea as to what went wrong. Okay, so we're going to try to grab on to port 8080 here. Fine. So at this point, if we're still kicking right here, that means we've done all of our initial setup. Because up until this point, we haven't actually hit the internet until right here. That's when we actually weren't even hitting the internet. We were hitting the local machine's port 8080 in this case and saying, I'm going to hold on to this guy. I'm binding to this port. This is my communication channel. Okay? Everything before this was set up for that to work. So if I'm still kicking right here, I have that port. My program here is bound to that port, and now it's mine. I don't have to worry about anybody else taking that port. Okay? So in other situations, let's say you had to find an available port. You might want to wrap this inside, actually, you wouldn't want to wrap that. You want to wrap this inside of maybe a loop that went through a collection of possible ports. Because you would want to check which is open. You might have to go through 15 or 20 ports to find out, especially if you're on a shared machine that has lots and lots and lots of users, and those users are all fighting for ports above port 1024. I mean, chances are you could probably find some opening. Right? But the point is that if you weren't guaranteed to have access to a specific port, doing a loop in there to try different ports might be something you needed to do. Okay? Finally, this guy right here is finally saying, if I'm still alive here, I have that port. It's mine. So now what I'm going to do is I'm going to start listening to this port. Here's my socket. Now the listen command takes in a 3. Let's see if I'm going to be able to conveniently. Yeah, here we go. So this takes in a socket and takes in something called a backlog. This parameter defines the maximum length for the queue of pending connections. So backlog means that this is more from a denial of service attack type thing. So how many connections can be sitting on this port trying to, because I think before I kind of said like this guy's sitting by the phone, incoming call comes in, he picks it up, probably is going to hand it off to somebody else. We're not doing threading yet here. But then he comes back here and listens again. This guy's going to allow 3 people to line up before it's going to start rejecting incoming connections. Okay? Which probably would not work for a Google web server, but for our little stupid thing here, it would be just fine. Okay? So when we get right here, we are now listening to port 8080, waiting for a connection. I'm going to say start here, right there. Real quick, in the book, where have we gone to in the book at this point? 1, 2, and 1, 2, and 9. Okay. We've done a bunch with 3, 4, 5. I would encourage you to at least gloss through 3, 4, and 5 just to see if there's any inner meaning in there. But let's, and as well as 6. We've already been using those things, but go ahead and work through that. But definitely maybe for Monday, why don't we look at structs? Because we've been talking about structs quite a bit. We're using a struct. So for Monday, do chapter 7 in the book. But I'd encourage you to at least leaf through 3, 4, 5, and 6. Okay? All right, I'll see everybody Monday.